Wunderbar. So that is our first one. Now let's take a look at parallel circuit. So on the screen, a parallel circuit, we know it contains more than one path for the current to flow. So the electrons can go either direction. They split. And if we remove one component in these, we still have a complete circuit in the other one, so that we don't get a short circuit. This is where most of your house is wired in parallel. So if a light bulb goes off, the whole house doesn't go dark. So we're going to take a look at this beauty, but this again would be another nice place to pause and write down the key concepts for a parallel circuit. So we know that the voltage across every parallel component is equal, and we can measure them. So we'll look at that in just a second. We'll also use a different resistance equation to calculate the total resistance. It is given by that equation on there, which can get a little bit dicey, so we'll go over that as well. So again, we want to calculate everything in our circuit puzzle. And this is for a parallel circuit. So a few things that we know. First, get out your testers. Here we go. Remember your voltage testers. This one is 15. This one measures 0. So anywhere along here, I haven't dropped my voltage anywhere. So everywhere up here, before we cross over a resistor, everywhere is 15 volts. Now if I bring my 0 down here, everywhere here is 0. So until I bump into one or cross one, my voltage is 0. So if I bring both of my voltage testers over to this one, that means 15 and 0. The voltage that's dropped across resistor 1 is 15 volts. That's always true of a parallel circuit. Same thing for resistor 2, 15, 0, and resistor 3, same thing. So we can go ahead and write all of those in on our circuit puzzle, but I'm going to hold off on that because we want to do the same thing. We want to collapse the circuit. And this is where it gets a little dicey. So when we collapse this, again, we want to simplify it so that we would only have to put in one resistor that would be equivalent to all three of these in parallel. So we have our initial voltage, 15 volts, and we want to find our total resistance, and we want to find our total current through all of those. And that'll give us plenty of information to fill out in the circuit puzzle. So the way that we do it, we use that equation. 1 over your total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And so what this means is that if, think of our traffic example again. If we have to go from work to home and we're going this way, if there are 3 traffic jams, well, if they're spread out in parallel, we have 3 different paths that we can take. We only have to go through one traffic jam. So imagine compared to this one, if this is the only path, we have this resistance, and if we open up another path, we could go to either one of those. So we have more paths to take. All of those electrons are spread out a little bit more. Now if we open up a third path, they have 3 options to go through. So we can get more current going out of here because we have 3 options to take. So the total resistance in a parallel circuit is going to be less than any one individual because there are more branches. So when we get this number, it should be lower than any one of those individual components. So let's go ahead and plug in our numbers and calculate. Now, when you get to this step, if you calculate this, you will, just as is, you will get 0.00289. And you might think, wow, the resistance really did go down. But remember that that is not the total resistance. What did we just solve for? We just solved for 1 over the total resistance. So we have to take the inverse of that. So 1 divided by that number, let's say, take the inverse, and we get 347 ohms. That is your total resistance. Great. So now that we have our voltage for the total current, or the total circuit, we have our resistance for the total circuit, we can calculate V equals IR to get our total current. So total voltage, total resistance gives us the total current. So I is equal to 15 volts divided by 347 ohms. Oops. And when we get this one done, we should get 0.006, oops, wrong problem, 0.0432 amps. So that's the total current. Okay, now it's time to write some things in our circuit puzzle down here because we know a lot of information now. So initially we said we know the voltage of each component. We did our voltage test. We had 15 volts, 15 volts, 15 volts. The voltage is all the same. That's always true of a parallel circuit because the total voltage was 15 volts. Now we know the individual components. We said the initial one was 470 ohms. Second one, 2200 ohms. Third one, 3300 ohms. And we just solved for that total. Notice that number, 347 ohms, is a lot lower than a few of these, but it's always going to be lower than all of them. Every single one. So total resistance is low. We just then calculated the total current, 0.0432 amps. But we don't know the current going through the individual components. So just like we did with the series circuit, once we know every bit of the total, we have to go back to the overall circuit and break it into each individual component. So we know the voltage across each one, we know the resistance of each one. Now we can plug it in to V equals IR. I'm going to go ahead and rearrange the equation because we want to figure out how much of that total current that leaves the battery goes through each one of those branches. So I equals V over R. And once again, this is where most people screw up. When we are calculating these, sometimes we may not use that 15 volts, so just double check. We want to make sure we have the voltage going across every component and the resistance of every single component. So when they get more complex, just make sure that when we're looking at the voltage for resistor 1, so voltage 1, resistance 1 gives us the current in branch 1. And we do. We know what those are. So the voltage is 15 volts in a parallel circuit, and the resistance was 470 ohms for that first one. So the current going through that first branch is going to be 0.0319 amps. So let's go ahead and write that down here. 0.0319 amps. Good. So two more, same exact process. So the current through branch 2 is equal to the voltage drop across the branch 2 and resistor 2. Voltage drop across resistor 2. So plug in those numbers. Voltage drop we know is 15 volts. Across resistor 2, 2200 ohms. The number that we come out with there, plug that into your calculator, you should get 0.0068 amps current. And double check that, compare the numbers. So we have more resistance, a lot more resistance in that branch, so a bigger traffic jam, so we have less current going through it, fewer cars, fewer electrons going through that branch. So let's go ahead and write that in our circuit puzzle. Now we only have one more. So same way, the current through that third branch is equal to the voltage drop divided by that resistance. So 15 volts divided by 3,300 ohms. Whoops, there we go. That is equal to 0.0045 amps. Write that in our circuit puzzle. Okay, and now it says to verify with Kirchhoff's law. So what do we know to be true? We know that all of this current coming out of here has to split between there, and there. And it's not splitting evenly, but it is splitting proportionally to the resistance in each one. You got more electrons flowing if the resistance is lower. So what we can do is we can add up these three currents. So the current through each branch has to be equal to the total. So you add this, and we should get that total current. That's a good way to verify that you've done it correctly. So this also helps if you don't want to calculate this 3 times, you can look back at your circuit puzzle and figure out a couple of different ways what you know and how to get that last bit of information. So we know the total current has to be equal to that plus that plus that. So if we're only missing one of those, we can just take our total current, subtract 2 of them, and hopefully we should get that third one. It's always a good idea to double check with the calculations so you know you're getting at least verification that you did something consistently. Whether it's right or not, different story. One more thing that we might look at is putting them in combination. So it's not always going to be 100% series or 100% parallel. We might see some where at the beginning we see all of the current going through this first battery, because from the battery to the first component, and then it has a split after that. So we have a little bit of parallel with 2 and 3, and then a little bit of series with 1 and 2. So how we would describe this, first of all, it's a combination circuit. Second of all, we would say that component 1, light bulb 1, is in series with the combination of 2 and 3. So all of the flow through light bulb number 1 has to go through both of 2 and 3 combined. So there are more complicated ways that we can break it down, like our circuit diagrams, but the principles are generally the same, and they get a lot more complicated. So in this picture, what would happen if you removed light 1? Well, since that's in series, all of the flow would stop because it's like flipping a switch. There's no path for it to take. What happened if we removed light 2 or 3? Well, since those are in parallel, there would still be another branch for them to flow through. So even though it would stop through that branch, we would still complete the circuit. All right, last one here. Our next unit is going to talk about power, and since we're on electricity, we know enough of the variables to calculate what power is used in electric components. So electric power is directly related to the amount of current and voltage within a system, measured in watts, and this is our equation. Power is equal to the current times the voltage, and that is for any component. So we could talk about the entire circuit, just like we were when we broke them down in the circuit puzzle, or we could say what is the power used by any one individual light bulb. And you know, you're familiar with these words watts because that's how we measure light bulbs. What is the wattage of that light bulb? That's the measure of the power used. And so it's how much current is flowing through that light bulb times the voltage of that light bulb. That's how they get those numbers. So again, if we know whatever the power is for that light bulb, we can calculate either or the other.